function that we talked about last time. So I call today's lesson, as I say, inverse logarithms. And to see what's coming up here, simply recall that last time we invented, so to speak, a new function called the natural log of x. This had nothing to do with exponents. It was what? This was the function whose derivative with respect to x was 1 over x and passed through the point 1, 0. That uniquely defined this particular function. The point being what? That this particular function, since the domain is for positive x, 1 over x is positive, the curve is always rising, which means that the function itself must be 1 to 1. And because the function is 1 to 1, it means that the inverse function exists. This is no different from any other example of forming f inverse given a 1-to-1 function called f. So what we do is now, and remember how you invert this function. If you want to do this thing in slow motion, you first rotate this through 90 degrees, then flip it over. If you want to do it faster, the inverse graph of this is the reflection of this curve with respect to the line y equals x. In any event, if we do this, we find that the graph of the function y equals inverse log x is this particular curve. And notice the correspondence. If this is the point 1, 0 on the log curve, the inverse point is 0, 1. In other words, the inverse log of 0 is 1. Okay. Now, the idea is something like this, just to have a review again of how, see, the punchline I want to make for today's lesson right at the beginning is that the nice thing about studying inverse functions is that once you know the function of which you're taking the inverse, you automatically get all the mileage you want out of the inverse function. Well, by way of illustration, if the function natural log had the usual logarithmic property, we would suspect that its inverse should have the usual exponential property. Now, what is the usual exponential property? The exponential function is characterized by what? That if you take f of x1 plus x2, that's f of x1 times f of x2. See, think of it in terms of the usual exponential notation. If you have, say, 10 raised to the x1 plus x2 power, that's the same as 10 to the x1 power times 10 to the x2 power. In other words, if our ln function is genuinely a logarithmic function, we would expect the inverse of that function to be a genuine exponential function. And just to work with inverses again, let's see if this is indeed true. Let's see if it's really true that the inverse log of x1 plus x2 is the inverse log of x1 times the inverse log of x2. See, the whole idea is what? Let's give these things names. Let y1 be the inverse log of x1 and y2 be the inverse log of x2. Now, since we've already studied the natural log function, the most natural thing to do here is to invert these. Namely, y1 equals the inverse natural log of x1 is the same as saying x1 is the natural log of y1. And similarly, this is the same as saying that x2 is the natural log of y2. And now we add equals to equals, and we get that x1 plus x2 is natural log y1 plus natural log y2. But allegedly, we understand the properties of the natural log, because if we didn't understand those, it would be kind of futile to be studying the inverse function. What do we know about the natural log? We know that the natural log of y1 times y2, by definition of a logarithmic function, is log y1 plus log y2. In other words, natural log y1 plus natural log y2, by the property of being logarithmic, is just the natural log of y1 times y2. And now taking this relationship and inverting it, to say this is the same as saying what? The inverse natural log of x1 plus x2 is equal to y1 times y2. And if you now observe that y1 was the inverse natural log of x1 and y2 is the inverse natural log of x2, we have the result that we claimed we would have at the beginning here. Now again, here's one example where it's not the result that I'm not interested in, but am interested in showing again what we meant when we said that once we learn a new concept, we can bring to it all of our